Okay, so thanks everyone for coming. I'm glad that you're here to listen to the talk. My name is Tim Oates. I'm a professor in the Computer Science and Electrical Engineering department at UMBC. I've been here for about 18 years, I guess now, so I feel like I've been around for kind of a long time. My areas of expertise are broadly artificial intelligence and machine learning. And actually back when I started in grad school, AI meant something different than it does now. I think when you say AI, it means machine learning. But back in the old days, I was doing symbolic AI kinds of things. And so today, what I'm going to do is I'm going to talk about some research that we've done recently. It's 2 algorithms for weakly supervised denoising of EEG data. So I'm going to spend the first part of the talk just kind of explaining what that means. I'll talk for, I don't know, an hour. We'll see how it goes. If you have any questions at any time, please feel free to interrupt. I suspect that there are very different levels of expertise on machine learning and the topics I'll be talking about. So, don't be shy about saying, hey, can you explain that in a little bit more detail? Before I get going, so every research project is a collaboration. I want to point out that Sunil Gandhi is a PhD student I'm working with. Sunil is sitting back there. Hey, Sunil, can you raise your hand? Yeah, there he is. Right. So, and he's going to graduate soon. So I thought it was actually interesting that Jason was saying everybody's hiring. So if you're looking for a very bright guy who knows a ton about machine learning and is an excellent communicator, go talk to Sunil after the talk. And I will. He did all the sort of like on the ground work here. And I'm actually going to try and delineate as I tell the story of this work. At some point I'll say, I feel like I kind of had intellectual ownership of some of the ideas, and then at some point Sunil was like, okay, those ideas are all right, but like I've got a better idea. And so the first half of the talk is our original direction on this research, and the second half was Sunil coming in and saying, hey, we can do a better job of it. So there are really three pieces to the talk, right? The first 3 items there. The first is I just want to talk about artifact removal from EEG data. I'll just sort of explode that. I'll explain what that means, why it's interesting, why we worked on it, what the challenges are. Then I'm going to introduce 2 different algorithms for solving that particular problem. The first approach is based on something called independent components analysis. We'll talk about what that is. And it uses a thing called MultiInstance Learning. We'll talk about what that is. We'll introduce both of those. And I'll describe that particular solution. It actually works pretty well. So that was the thing that we originally started out with, and this work was funded by the Army Research Lab. And I'll tell you why they care about that problem. And then we said, okay, that was fun, but the thing that we built was a little bit of a Frankenstein. So as you'll see, it's got just a bunch of different pieces that kind of have to work together. And the second approach goes, which is what every graduate student wants to do these days, is they want to build an end-to-end deep network that solves the entire problem. So Sunil came along and went, I'm going to do that, and he actually succeeded in doing it. So that's the story that we're going to tell, and I don't know, maybe there'll be future work or not, I'm not sure, and please ask questions as we go along. So the first thing I want to do is just introduce this notion of electroencephalography, or EEG. So it's used to record electrical activity in the brain. And actually that picture is a really good one, because when we first started working on this particular project, we were working with people in the neuroscience department at the University of Maryland Medical School, and they do a lot of clinical studies of people who have various neurological disorders, so epilepsy being one of them. And it turns out that the appropriate treatment for you when you have epilepsy is dependent on the kind of seizures that you have. So they'll often have you come into a clinical setting, spend 24 hours there. They'll put a headset on that looks a lot like that. And what it's doing is you've got these electrodes that are connected to your scalp, and they are very careful about, they put the electrodes in specific locations. They actually have a gel, a conductive gel that makes sure that that electrode is touching your skin. And they're careful about, as you move around to make sure that they're not wobbling too much. And so what the electrodes do is they record electrical activity in the brain. So you get this fairly high resolution signal, several hundred hertz, and every one of those electrodes is producing a waveform, and you can see an example of it there. Now, interestingly, as you might expect, electrodes that are close to one another on the scalp are kind of correlated with one another, but you can see different behavior as the electrodes are put at different locations on the head. So what we're doing is, your brain, as you're doing all kinds of things, is generating electrical activity, and what we'd like to do is to get a window into what's happening in your brain for lots of different applications. So that's EEG. One of the projects that we worked on, and actually here are a bunch of collaborators, I would like to point out Tinush Mohseni down there on the end. She is a computer engineer in our department who focuses on low power, efficient hardware. And so what we do is we tend to build machine learning algorithms, and then what she does is she takes those things and then figures out how to actually make them work on very sort of small, lightweight platforms that can be deployed out into the field. So the original thing that we were thinking about was seizure detection, and this will become important a little bit later. And the thing that we were thinking about was doing seizure detection in an ambulatory setting. So I'm not in a hospital in a clinical setting, but imagine you have a child, for example, that has epilepsy, and they might have a seizure at night. And so what we'd like to do is to allow them to wear sort of a lightweight, maybe a cap that looks a little bit more like that, not like the one on the previous slide. They can wear that at night. We can be monitoring their brain activity. And if they have a seizure, if we can detect that they're in the midst of having a seizure, then we can send help, right? You can alert the parent, you can alert a caregiver or something like that. And the issue that's going to come up is that, if I'm lying in bed, and what we're going to talk about with artifacts is that there's all kinds of noise that gets introduced. So basically, every movement that you make, if I'm standing up here moving around like this, I'm introducing noise into that EEG signal. And so we're really interested in being able to deal with that. There is also work on determining cognitive load. So the military funds, interestingly enough, the military funds a lot of this work. There's a group, as I said, this was funded by the Army Research Lab up at Aberdeen Proving Ground. They've got a group of about 40 neuroscientists that are sitting up there, which was a real shock to me. But they're really interested in things like, is the warfighter being overloaded cognitively right now? I need to have someone who, if I'm completely stressed out and I'm not able to focus and process information, maybe I need to back off on you a little bit and let you get your wits about you before I give you more work to do. So determining cognitive load is another one. Brain-computer interfaces is another one. So I will say Sunil got this video. I think it's wonderful. I don't know if you're not going to be able to hear it. Actually, the only sound that you're going to hear is a drone. So this guy sitting right here has got a headset on. There's a drone. I think there's a drone sitting on the table. And what he's going to do is control the drone with his brain, right? So he's wearing a headset. I would like to point out that it looks like the professor who's directing it is very safely tucked behind that cabinet right there. These other students out here, they're open in the line of fire. So basically, this guy is thinking, I want the drone to go to this location. And I think now he's trying to make it go over to the left. He's trying. In a minute, it'll go that way. That guy looks like he feels pretty safe. That guy, he's not sure. All right, and it drops, right? So again, that was done exactly using this EEG technology, which is simply recording the electrical activity in the brain. All right, so that's another application. And then another one of our collaborators, Dave Harrison, works at ARL, and they're interested in things like driver drowsiness, right? So I've got people in the military driving trucks around. I'd like to know if they're getting sleepy so that they don't wind up having accidents or having wrecks. So there are lots of really good applications of this. So what are the challenges? One is that, as you saw that first slide, right? So that headset that probably had 64 electrodes on it, and like, I can't imagine, that guy looked so uncomfortable, right? I think he was trying not to look uncomfortable, but it just looked miserable. So there is a lack of kind of comfortable headsets. Now, there is a company called Emotive that produces this headset. I actually bought one, I don't know, maybe 10 years ago. I have to say 10 years ago, I wasn't very thrilled with the quality of it, right? So there's this trade-off between, I'm going to have this thing that looks okay, like I might actually wear it out in public, or, you know, if I go out, you know, like if I can make metal move with my mind, I can wear that thing out in public and you know, nobody's going to mess with me. But your average Joe out in public doesn't want to walk around with this giant headset on. The other problem, the one that we're going to deal with, is this idea of noisy data. So again, if I'm in a clinical setting and I'm quiet and I have nurses around to help keep the headsets on properly, I'm not going to have issues. But as soon as I start doing anything, I'm going to induce a lot of noise. And that's the challenge that we're going to focus on. The other is just, you know, having these online automated algorithms. So can I, in a real-time setting, detect, for example, that someone's having a seizure and send help to them? And then these hardware implementations are a thing that we're interested in our research group. I'm not going to talk about that as much today, but it's important that the algorithms be efficient. Okay, so what are artifacts? So an artifact is just some unwanted electrical activity from sources other than the brain. It turns out that there are sort of two different kinds. There are external artifacts. So if I'm moving, notice in that first slide, there were wires everywhere. So I'm going to move around, and as those wires move, the electrodes move, and it induces some additional potentials in there. There can be also external device artifacts. So one kind of artifact that you'll often see is 60 hertz noise. Where's that coming from? That's coming from, I've got power outlets around me, right? There's electrical equipment that's just adding that signal in there. Now, interestingly, there's some great work on being able to get rid of external artifacts. So there's a guy who had what I thought was a genius idea, which is you put the headset on, and then you put like another conducting cap on top of that. And you can measure motion from that conducting cap. So essentially, as I'm moving around, the electrode's pointing up and down, I go, oh, I'm recording movement here. I'm going to subtract that out from the signal that's here, right? So there's some work along those lines. The thing that's really hard is biological artifacts. So if you talk, if you chew gum, if your heart beats, which hopefully is happening all the time, if you blink your eyes, if you sneeze, right? If I lift something, all of those things are inducing electrical potentials in your body, and they wind up showing up in the EEG. So artifacts are just a huge problem. Here's a really simple example. Here's your standard EEG. It's a montage that's commonly used, and these are just me blinking, right? So you induce these huge changes in those potentials. Now, it's really tempting, I think, to look at that and go, well, that can't be that hard, right? That is completely obvious to me that there's something going on there. And I gotta say, that was my attitude very early on in this project, but it turns out it's real hard. So, you know, just because what we'll find, what you'll see later is that my eye blinks look different from your eye blinks, and when I blink from, you know, today to tomorrow, it looks different. So it's just a really hard problem to try and extract all that information. So, anyway, so why is it important to remove them? Increase the chances of false alarms and seizure detection, right? So I don't want it to be the case that, you know, my child coughs and I get an alert saying that they're having a seizure, right? They could also alter the shape of neurological events causing unintentional control of BCI systems, right? So that drone might slam into your head because I blinked, and that seems like a bad thing. So we really want to try and get rid of those things. Again, these external artifacts, you can kind of control the external environment to some extent, but you can't avoid biological artifacts. You're going to breathe, you're going to blink, you're going to be eating things. There's nothing you can do. You just can't make them go away. So what you have to do is you have to do something algorithmic on it. So we did the following things, and I'm going to talk about the first two today. So a lot of past work on removing artifacts from EEG data was very supervised in nature. So what it meant was, I would say, okay, I'm going to get you to sit there, and actually we have a data set like this that we used, and I would like you to sit still and then blink your eyes, and then sit still and blink your eyes. And what I'll do is I'll go, okay, I know you're blinking your eyes here, you're not here, you're blinking your eyes here. So now what I've got is I've got a labeled data set, and I can train up a system to go, oh, I blink, right? What we'd like to do is to not necessarily have to say, we're going to gather that supervisory information. What we said was, imagine we can just go, we think there's an artifact of some kind, right? We don't know if it's eye blinking, so maybe what you can do is you can use a bone-conducting microphone that can just hear things when I'm talking or chewing or sneezing or whatever, and go, oh, something's going on, there's probably an artifact, right? That's weak supervisory information, so we built that system. And then what we did, so the sort of second innovation was to build this sort of end-to-end online neural network that just goes, hey, you give me a bunch of EEG data that's clean, you give me a bunch of EEG data that's known to have artifacts, I'm going to figure out how to remove the artifact, right? Just good data, bad data, and the network's going to sort it out. So that's where we're going to go for the rest of the talk. And I'll talk about related work just very briefly. But are we good to go? That's kind of the first bit of the talk. Does that all make sense? Any questions? Yeah? Okay. Yeah, that all I think is pretty reasonable. So again, a lot of our work was this sort of supervised methodology. You're going to train an artifact detector. So what some people would do is they would train an artifact detector and go, oh, I can recognize eye blinks. Oh, you just blinked your eyes, boom, I'm just going to cut that segment out of the EEG. What that means is I've just lost all that signal, right? So if that signal is important, for example, I'm engaged in a BCI task, it's gone. The other thing that people have done is they'll get these reference channels. So you've got electrocardiography, which is I'm going to put an ECG on you and I'll know when your heart is beating. And so I can just follow that signal and go, oh, that's the heartbeat. Let me try and back that out using a regression method. Electrooculography is I'm going to put sensors around the eyes so I can tell when you're moving your eyes around. And electromyography is just testing, is identifying I'm moving, right? So I'm trying to find that you're abusing your muscles. That's generating electrical potentials. So all these things can say, well, I'll put an additional sensor on there, and then I'll try and say, okay, that's generating noise, let me try and back that out. But it requires that reference signal. So we try to be a little bit more general than that. Yep.
Just a quick question. Do artifacts ignore each other? Like if you blink and chew gum at the same time, does the blinking still look like a blinking on top of chewing gum?
Right. So that's right. So if I blink and chew gum at the same time, so I'm chewing gum, right, I get that chewing gum artifact, the blinking is going to ride on top of it. And it definitely is not the case that it's going to look necessarily like that I can go, oh, you're blinking and chewing gum at the same time. They're going to add together in certain interesting ways. And actually, there'll be a slide in a minute that will shed a little bit of insight into why that is. Yeah. Okay. Yep.
Before the data it look like the data is over time. Do you know somebody tried a time series model for you?
Yes. Yeah. So time series model. So it's all temporal data. So actually, this bit of related work here does something like that. So there's a thing called a wavelet transform, and so essentially you can try and apply digital filtering to it. So these guys, what they did was they took that time series and kind of pulled it apart into the different frequencies and said, oh, the noise is lower frequency than that sort of high frequency brain activity, let me get rid of that, right? And then actually what you're going to see in a minute is that we're going to treat it as kind of a time series problem, right? So people have definitely thought about it in terms of temporal data, and it really is data through time. Okay? Okay, good. I like that. I like questions. I get bored listening to myself talk. So, okay, so I just want to put this slide up here. Let's talk about it for just a second, because this is actually going to help us kind of understand the application of these principal components analysis and independent components analysis. So there's this thing called blind source separation, and it works like this. So we've got a whole bunch of sources of audio, right? So let's think about audio for just a second. There's a police siren, there's a TV. Does that face look familiar to anybody, that third one? I think it was, Tip O'Neill? Is it Tip O'Neill? Yeah. That's what I thought. Okay, right. It's all of us who are a little bit older that know who that is. So you've got all these sounds going on. So let's imagine that you've also got a number of microphones that are placed around, right? Now, each of those microphones, so if the microphone is right here, it's going to get all those waveforms coming together, and it's going to kind of hear them slightly differently because of its position. Another microphone sitting over there is going to get all those sounds coming together, but it's going to have a slightly different perspective on it because of where it sits physically. And the blind source separation problem goes, okay, I want to take all those microphones that are kind of hearing all this junk going on around at the same time, and I want to separate out the individual signals. Okay, now, what does that have to do with your brain? Think about it this way. This is your brain, right? So your brain has lots of different centers of activity. You know, you've got your left brain and your right brain, and you've got your visual cortex and your auditory cortex. And so everything that you're doing is sort of lighting up different parts of your brain. Those microphones are in some sense the electrodes that are sitting on top of your head, right? So they're kind of, like I got an electrode right here, but it's not listening to the part of my brain that's just underneath it. It turns out that your skull and sort of all the fluid in there is kind of capturing all that electrical activity and bringing it together in that one point. And so this electrode gets a view onto it, this electrode gets a different view onto it. And so what we'd like to do then is to take all those electrodes and somehow kind of pull apart those signals underneath it, right? We'd like to get to what is the underlying brain activity. So one method for taking a bunch of signals and then trying to pull them apart into components is principal components analysis. If you don't know what it is, it's fine. All it does is it says, I'm going to come up with a linear combination of my base signals that captures a lot of the variation in the data, and then I'm going to come up with another linear combination that is orthogonal at 90 degrees to it. And it just keeps pulling out these principal components that are trying to capture the variation. Unfortunately, PCA is not good, right? So people started doing that, and PCA is not the right way to go. However, there's a thing called independent components analysis that works unbelievably well in being able to do this. So what independent components analysis does is it says, I want to take these sort of microphones that I'm listening to, and I want to represent what I'm hearing as a combination of signals that are independent of one another, that are statistically independent. So if you guys are having a conversation and you guys are having a conversation, then the noise I'm hearing over here is independent of the noise I'm hearing over here, right? What I hear you talking about doesn't convey any information about what these guys are talking about, right? So that is the sense in which they are statistically independent of one another. So the thought is that those independent components, like what's happening here is independent of what's happening here in the brain, but I kind of see mixtures of that in the EEG data. So independent components analysis works unbelievably well. There are tons of papers about that. However, one downside is the artifact components need to be manually identified. And you train up a supervised classifier to do that. Now, why is that? So notice, here, let's imagine that all the activity that's shown up here is actual good brain activity, except for the piano at the bottom. That's the noise. That's the artifact, right? ICA can separate that out, but it doesn't go. ICA doesn't say, oh, and by the way, here's the noise. It just goes, here's here's a signal, and it's up to you to figure out which one is the artifact. So a lot of this work is just like that. It goes, okay, I'm going to use ICA, and I'm going to have a human go in and go, that's the artifact, that's the artifact, that's the artifact, and I'm going to train up the supervised classifier. So what we did was we said, can we just use a sort of weak supervisory signal that says, we got some noisy data, we got some clean data, we're not going to go in and manually identify where these things are and train up the system to do it. Okay, so here's the first system architecture. Okay, I was just checking my time. All right, so here's the architecture. What this sequence of slides is going to do is it is just going to introduce the various components. So let me just say a couple of words about this, and then the next slides are going to look at the ICA part, the SACS feature extraction, and the multi-instance learning. This is actually the kind of idea that we originally proposed to the Army, that we said we thought this would work. It turns out it works. But as you're going to see, it's just got a lot of pieces that get plugged together, and our goal is to be able to make it work efficiently on low-power hardware so that you can have warfighters or children sleeping in bed not have to be hooked up to like a 5-pound battery, right? But you could do it with a lighter battery and a simple processing element. So essentially what we do is we take the EEG data, we got all these channels, so 64 channels is actually pretty common, so I'm going to have 64 electrodes stuck to my head. I'm going to pass that through ICA. What ICA is going to do is it's going to take all those sort of views on your brain activity and try and pull it apart into these 64 independent components. The hope is that 63 of those correspond to actual sort of distinct things going on in your brain, and the 64th is noise. We don't know where it's going to be in that list, right? But we're going to say there's a noise signal that gets pulled out. Then what we're going to do is we're going to hand that off to stacks, which is a way of kind of turning time series into feature vectors, and then we're going to hand that off to multi-instance learning. All right, and then out the back end of this thing is we're going to take every single one of those components that were found by ICA and attach to it a probability that it's noise. All right? Does that make sense? I got a couple of frowns out there like, I don't know what you're talking about right now, but are we okay? I mean, ask questions. Okay, all right. Okay, so again, remember, independent components analysis goes, look, we've got some original signals, we've got the red one, the green one, and the blue one. It goes into this mixing system, which is, it's like a microphone listening to these three things happening. It's an electrode sitting on your head. It's sort of got views of three different things going on in your brain. And it produces these observed signals. So in this case, I've got 3 electrodes and they're observing stuff. We hand it to ICA. The idea is that ICA is then going to sort of pull back apart those individual components. So we're going to go from brain activity to the thing that we can observe, right? All the way back out to the signals that actually generated those observations. Now, the interesting thing, and again, so Sunil created these slides, I have to confess. And so this slide's beautiful for the following reason, right? It shows that, look, we've got a red, green, and the blue, but they come out on this end, and ICA just goes, I found 3 signals, right? There's no notion of order to them or anything. Just, well, we found these 3 signals. So here's an example of it. This is actually taken from Scikit-learn's examples of ICA for blind source separation. So notice that on the top, you've got these mixed signals, which are linear combinations of the true sources. So we've got like a sine wave, a sawtooth wave, and a square wave. And what ICA does is it takes those mixed signals and then says, okay, I think the underlying true sources are the ones down on the 3rd row, right? And it does a really good job of going, oh, there's something that looks a lot like a sine wave, there's something that looks a lot like a sawtooth wave and a square wave. However, the colors are different, right? Because again, it doesn't know that there's a one-to-one mapping between those 2 things. And then PCA just fails, right? So PCA is not good for it. So what we do then is to say, all right, we've got the clean EEG signal in an artifact. That goes into a mixing system, right? Which is your brain's doing stuff and there's noise coming because I'm blinking or talking or whatever. We get the observed signals, and we would like ICA to sort of pull these things apart for us. All right? That's that part of it. Now, okay, so what? Yes?
So you're using 64 channels here, but you don't know if there are 64 independent real sources in the brain. You don't know how many.
That's exactly right.
So how does it work when you don't know how many? And do you subsample to...
Nah, so it's very standard, right? So you're exactly right. So I don't know. I'd like to think I have more than 64 things going on in my brain, right? So it could be that there are 30 things or 32 things. So, but it's just very standard to say I've got some resolution. I've got 32, 64, 128 sensors, and I'm going to pull those things apart and hope that for whatever the downstream task is, whatever resolution I'm getting is sufficient for that task, right? It's very common, though, to believe that one of those things that's coming out is going to represent the noise. So it doesn't matter, so on some level what I'm saying is it doesn't matter if I've got too much resolution or too little resolution up here with respect to what's really happening in the brain, as long as I get enough information to be able to fly the drone or to figure out if you're sleepy or something like that. Does that answer your question?
Yeah.
Yeah, okay. Yeah.
So it seems like because there isn't an ordering,
Yes.
that the noise component could change over time?
Absolutely.
Is that something where you do like a windowing to see where it goes to?
That's why we use multi-instance learning. That's exactly the problem, right? Is like, I'm running it, so for me today, my noise signal gets pulled out as signal 3, yours is coming out as 10, and tomorrow mine is channel 50, right? So the problem is that we get these signals that are coming out of ICA, and we like, I don't know, where's the noise, right? So multi-instance learning is going to solve that problem for us. Yeah. I feel like I saw another, no? Okay, all right, let's keep going. So, so here's the, okay, so SAT. All right, so here's the story so far, right? So what we've done is we've said, we got all these sensors that are seeing mixtures of brain activity. We use ICA, which is really good at pulling those things apart, right? So now we go, okay, fine, we've kind of recovered the signals that are going on in the brain, and we've got a noise signal. But now what we need to do is to try and figure out, like you were saying, is, I don't know, which one of those is the noise signal? So what we're going to do is we're going to apply standard classification techniques. And to do that, what we wound up doing was simply taking the time series and turning them into, and discretizing them. Using a very clever method called SAX. I think I'm not going to describe too carefully, but think about it this way. What SAX does is it takes a window, runs it over the time series, and for every one of those windows, it converts it into a word, right? So, and I can tell you, if you want to come up afterwards, and I'll be glad to tell you about SAX. So in essence, what SAX does is it takes a time series and turns it into a bag of words, right? So it turns it into kind of a document, and I can count how often certain little local patterns occur there. So it's essentially saying, here's a local pattern, I'm going to represent that by B, A, B, C, C, B, C, right? A different pattern is going to have a different sequence of characters associated with it. And so now we've got is this sort of vectorized representation that we can hand off to any standard machine learning algorithm. Okay, so now we've gone brain activity to the signals that are actually kind of happening in the brain to feature vectors. So now we've got 64 feature vectors. One of them corresponds to noise. And so the question is, how do we find that particular thing? So we wound up using this thing called MultiInstance Learning. Yeah, I don't know how common, that's a real low resolution, especially when it's this big, it's very low resolution. So here's the idea. So in standard supervised learning, I go, here's an instance, and my favorite example is mushrooms, right? So here's a mushroom, it will kill you if you eat it, right? So this thing is poisonous. Here's another mushroom, it is edible, right? So I have a thing and a class label associated with it. In multi-instance learning, what you wind up with is a bag of instances. So I throw a whole bunch of mushrooms into the bag, and if any of those mushrooms are poisonous, that's a poisonous bag. I just need one poisonous mushroom for it to be poisonous, right? If I have a whole bunch of mushrooms in there, and every single one of those is edible, it's an edible bag. So where does that come up? What does this mean here? So imagine what I do is I go to a search engine and I put in a query for face, right? So I'm looking for images of faces. If you go to Google and do that, I'm assuming you're going to get back lots of pictures of faces, but you know how search engines are. They're going to return pictures that don't have faces in them. Maybe it's the face of a die or something like that, or the face of a card or something. So in those results there are going to be some faces and some not faces, right? Then you can have these other sets of images that you've gotten through other queries that you think don't have faces in them. So I can issue a face query, and I know somewhere in there there's a face, right? I can issue another query, and in here there's no faces. So now what I've got is I've got a bag of images and a bag of images. This one is a positive bag because there's a face in there somewhere, right? This is a negative bag. So how do we apply multi-instance learning in this particular case? What we do, so again, this is the idea, is that bags are labeled positive or negative. If a bag contains at least one positive instance, it's a positive bag. And if it contains no positive instances, it's a negative bag. So hold on. Okay, hold on. Okay, so let me just say this. So what we're going to do then is we are going to take EEG data where we know that there's noise in it, right? So somebody's come along and said, yeah, there's noise in here from whatever source. Like we don't have to have knowledge about where the noise occurs. We don't need to have any idea about what kind of noise it is. You could be chewing, or talking, or sneezing, or snoring, or coughing, or whatever. Just like something happened in that EEG signal. There's noise in there. In this other data, we're saying this person was sitting still, there's no noise, right? So now what we can do is we can run ICA on the EEG that's noisy And we know that one of those components that pops out corresponds to noise, right? So now I've got a bag where the signals in there that correspond to brain activity are negative examples, and we've got that one positive example of noise. And then we've got the clean EEG, where everything just corresponds to signal, and there's no noise component in there. So we've got a positive bag here, which has noise. We have a negative bag here, which does not have noise. All right? So what multi-instance learning does is it learns to say, all right, what I'm going to do is I'm going to learn to classify bags as positive or negative, and by virtue of doing that, I can look at the instances inside there and tell you whether the instances are positive or negative. So multi-instance learning, when it's trained up, is going to allow us to go, okay, here are a bunch of ICA extracted components. Tell me if any of these guys are noise or not. Right? So that solves the problem of us having no idea what the ordering is. Okay, that was a lot of information, and I'm actually getting ready to talk about results. So are there questions? Like just on the algorithm and the approach? Yeah.
The very last part is said that there's a gap for me.
Okay.
So the back and the low back makes sense. But how do you jump into, if there's at least one in this bag, how do you jump into like which instance is noise and not?
Oh, okay, good. So let me give you one example of a multi-instance algorithm. And Sunil's going to correct me if I say this wrong. All right. So one algorithm works like this. And I can't remember which, it's MISV, either lowercase or uppercase, and we'll see this in a second. So what I could do is if I've got, so let's say this is a positive bag, like everybody here is this is a positive bag, that means somebody in this area is a positive instance. This is a negative bag, there are no positive instances here. I think the way one of the algorithms works is it does like this, it goes, all right, I'm just going to pretend all you guys are positive, and I'm looking at Sunil, maybe he's shaking his head. I'm going to pretend all you guys are positive, and I'm going to say all you guys are negative, and I'm just going to train up a supervised classifier to tell you guys apart. So, and one algorithm that's used is a support vector machine. Now, of course, it's wrong about, like, that's wrong because most of the people in this area are negative instances, but there's a positive one in here. All it needs is a little bit of signal to latch onto. Then what I can do is I can just apply that classifier to all the instances in a bag, and it will sort of bump up for the one that's actually positive. It'll go, yeah, it's probably more likely that's a positive instance. Now that's a real bad coarse approximation, but that's one method of doing it, is essentially just pretending you're all positive, you're all negative, training up a supervised classifier, hoping that there are enough positive instances lying around in the positive bags that thing can just start to kind of pull it apart a little bit. Did I say it? Yeah? Okay, good. All right, good. That's awesome. There are much more sophisticated algorithms for doing it. Like that's just sort of it's not dumb, right? But it's like, okay, let's just try this thing and see if it works. It turns out it works well. There are more sophisticated ones. Basically, they all boil down to the following thing. They're essentially all just trying to do density estimation. So what I'm going to do is I'm going to look at the density of points, right? So I'm just going to do density estimation. All the instances, you know, they sit in that instance space with certain densities. And then I look at the positive bags and say, are there any points in that space that seem to be a little overrepresented in the positive bags, right? So those places where the density of points in the positive bags are somewhat different from what they are in the negative bags, those are the areas in the instance space that start looking like positives. Okay? Yeah, okay. All right. Okay. All right, let me keep going. I want to talk about, all right. I'll talk about the results. So, and then I want to talk about the GAN stuff for a little while. So, we got this data set from the Army Research Lab. They actually, so the great thing about being in the Army is they can force soldiers to do things, right? So they can say, hey, you're going to go here and we're going to gather this data on you. And so what they did was they got them to sit there and they do things like say, all right, you're going to sit there and we're going to play a tone or something. I can't remember what it was. But every 2 seconds, you're going to clench your jaw and release, right? So you're just going to sit there, clench, release, wait a little while, clench, release, right? Clench your jaw, move your jaw vertically, blink. And apparently not squinting is super important. You're going to move the eyes left or up and down, raise and lower your eyebrows. Actually, Sunil's done a ton of work on the eyebrow data set. Rotate your head, shrug your shoulders, stuff like that. Like that kind of stuff induces artifacts. So we've got all these artifacts in there. There's an example on the left-hand side of actual EEG when you're not doing anything. And there you are raising and lowering your eyebrows, right? So we apply these algorithms. So it turns out that there are a bunch of SVM approaches to multi-instance learning. You've got your lowercase MI-SVM, you've got your uppercase MI-SVM. No idea what the difference is. Sunil probably knows, I have no idea. And then there's this normalized set kernel. Notice that we can have different kernels, we can have linear kernels and quadratic kernels. And what we wound up finding was that that normalized set kernel with the linear kernel actually gave us an accuracy of 95.2% in terms of identifying the noise. So that is the noise component. So this particular approach actually gave us quite good results. One thing I also want to point out is that we looked at a couple of different things. We did what's called leave one subject out accuracy, right? So what that means is we have, I don't know, on the order of 20 patients. That's order of magnitude correct. So what we would do is we train the classifier on 19 of them, right? And then say, hey, can we identify artifacts in this other patient that was held out? The other thing we would do is we would do personalized accuracy, which is we would take, we've got several hours of your EEG data, we would train it up on part of it, and then test it on the other part. Now, as you might suspect, you can actually get higher personalized accuracy. So again, my brain activity is different from your brain activity. And even I think there was a patient in here where they did EEG, maybe that was in an earlier data set, not the Army data set, maybe it was a hospital data set where they had a patient come in and then a year later they came in and got tested again, completely bombed, right? We could train on you in 2018 and test you in 2019 and it just doesn't translate well at all. I will point out though that our colleagues, again, Dave Hairston was this guy that we collaborated with, they did this thing where they were using supervised machine learning methods to solve the same problem. And their accuracy was, like comparable, right? Sometimes they were better, but other times they were worse. And what we're doing is we're using much less information than they are, right? They were training up supervised classifiers. Okay, so what I want to do is, let me just launch in. I'll spend just a few more minutes talking about sort of the neural net approach to this. So this was good, right? So I feel like this was very successful, actually. Again, there's a whole bunch of, so there's Sunil, I'm in there, Dave Harrison's in there, Tanush is in there. So again, we published this stuff. We actually wound up, I feel like this was in circuits and systems, right? So we both developed the system, and then the computer engineers who were in here took that and applied it on, some low power hardware. I think they had some Jetsons, and I can't remember, maybe some FPGAs and things like that to try and make it efficient. So the problem though is, quite frankly, it was painful, right? So you've got ICA, you've got SACs, you've got multi-instance learning, and I will say the computer engineers were not happy, right? Because they had to get all that stuff running, and I can't remember if there was some Python that had to be running, and they just didn't like it at all. So the idea was, can we build an indent system? And so Sunil actually went off and sort of thought real hard about this and came up with an approach which was based on generative adversarial networks. So I'll spend a little bit of time talking about that. I'll briefly talk about GANs and cycle GANs, and then we'll talk about his implementation. I will say that my experience with GANs, if you know GANs, is that they're a lot like finicky cats. So I've got cats, I love cats, right? But sometimes I'll put a bowl of, like my cat will act like it's starving. I'll put a bowl of food out and it will literally walk away, right? And I feel like GANs are like that, right? They're very finicky. You can say, I've got this architecture all set up to learn this problem, and the GAN will go, oh, I don't think I'm interested in helping you right now. And so there was a lot of fighting with the GANs that went on. However, I think, we got good results on this. So what is a generative adversarial network? This is just sort of like a really clever idea that goes like this. So it's a neural network architecture, and you've got two networks. You've got this thing called a generator, and you've got a discriminator. So what the generator does is it's going to take some input, and it could just be random noise, right? So I'm just going to give you some random noise. I'm going to take that as an input, and what I would like to do is to produce an output that looks like a cat, right? So how do I do that, right? It seems hard to think about how you're going to make it do that. The key intuition was, all right, well, what I'm going to do is I'm also going to train up a discriminator to try and figure out, is the cat that you gave me a real cat, or is it a generated cat? Did you create that cat, or was that a cat picture that was taken in practice? So what I'm going to do in the whole sort of like neural net way is to actually take my errors here and back propagate them all the way back through to the generator network so that I can tune the generator network to get better and better at fooling the discriminator. So the setup looks like this. The generator is going to go, okay, hey, I got some random noise, I generated a cat. And of course, it's not going to look anything like a cat when it first starts out. And it'll generate this fake image, and you hand it to the discriminator. Now note that the discriminator has to be trained up to tell the difference between fake cats and real cats. So I'm going to get pictures of real cats. I'm going to say, hey, discriminator, here's a picture of a cat I found on the internet. That's real. And then I'm going to go, generator, please generate an image. And it will go, here's a generated image. Looks nothing like a cat. And hey, discriminator, that's a fake cat. So I'm training the discriminator to tell the difference between real and fake cats. And what I'm doing is I'm all the while using this guy's results to make the discriminator try and get better and better at fooling the generator to get better and better at fooling the discriminator. So it's this sort of, it's an adversarial network because there's a sort of a battle going on, right? The generator is trying to get good at fooling the discriminator, and the discriminator is trying to get good at telling what the generator is doing. And so what you find over time is that the generator gets better and better at generating pictures of cats, right? So now you think, okay, why do we need cats, right? Why do we need pictures of cats? So maybe you've seen some results like this. What they did was they took that idea and said, okay, what if we have unpaired image collection? So maybe I've got a whole bunch of pictures of zebras and a whole bunch of pictures of horses, right? They're not paired, and let me just give you the quick preview. The reason this is going to be relevant to the EEG stuff is I might have a whole bunch of clean EEG data, and I might have a whole bunch of noisy EEG data, but I don't have denoised noisy EEG data because that presumes that we've already solved the problem, right? So in this case, what they said was, can we build a network that takes a bunch of pictures of zebras and a bunch of pictures of horses and learns to take that zebra picture and turn it into a horse picture, right? Or can I take that horse and turn it into a zebra, and can I go the other way? They've also done it for taking photographs and turning them into sort of the painting styles of various artists. And I think you can do this on your cell phone, right? Can you do this on your phone? Yeah, okay, right. Yeah, I would not know. My 13-year-old would know. So, I'm sorry, she's not 13. She just turned 15. Okay, so they use this thing that's called a cycle GAN, and that's the thing that we wound up using. And a cycle GAN has these two functions. So you've got this one domain X, which is horses. You've got this other domain Y, which is zebras. And so I'm going to try and learn a function that takes a picture of a horse and turns it into a picture of a zebra. That's G of X. And then I'm going to have another function F that takes a zebra and turns it into a picture of a horse. That's F of Y. And I'm going to have discriminators on both sides, right? Because they're both sitting there saying, right, like, I'm going to be able to tell the difference. You give me a real zebra or a fake zebra, and I'm going to figure it out. And those three networks, or four networks, are going to start working and competing with one another and try and learn that map. Now, the cycle GAN idea is as follows, right? So one thing that I could do as a generator is I could say, like, I forgot this learning stuff. I'm just going to memorize 5 pictures of horses, and I'm just going to give you a horse, right? Like, here's a horse, and it looks very realistic, and the discriminator will go, indeed, that does look realistic. You win, right? But the problem is that if I just give you a picture of a horse, it might have nothing to do with the picture of the zebra that came in, right? What we really want is that picture of a zebra with the zebra sort of turned so that it looks like a horse in the context where it currently is. So the cycle GAN idea says, all right, here's what we'll do, is we will take that horse and turn it into a zebra and then make it go back into horse space, right? So we're going to do a cycle through this thing. I'm going to go through G and F, and it should be the case that when I go from horse to zebra back to horse, those two horses are similar, right? Like the original horse looks a lot like the horse that I sort of recovered. What that ensures is that the picture sort of looks the same as it goes through, right? I can't take a picture of a horse in a zoo. Horses aren't in zoos. I can't take a picture of a zebra in a zoo, turn it into a horse in a pasture, right? Because if I go from zebra in zoo to horse in pasture, I'm not going to be able to come back to the zebra in the zoo. So I've got to kind of keep things consistent structurally as I go through. So they have this sort of forward cycle loss and the reverse cycle. So we go from horse to zebra to horse, and from zebra to horse to 0. Okay? And I'm going a little bit fast now because you've been unbelievably patient, and I'll stop soon. So here's what we're going to do, is we're going to do exactly the same kind of thing, which is we've got a whole bunch of EEG data, which is noisy, and then we've got some other EEG data without artifacts, but they're not paired up, right? So what we might like to do is do this CycleGAN thing, which says, oh, here's some noisy EEG data. Can I learn to map that noisy EEG data domain to the noise-free EEG data domain and back, right? Now the beauty of that is that it's just sort of, it's all neural networks, top to bottom. You can train it up end to end. The difficulty is that it was real painful and painful, right? So what we wound up doing was to do exactly the CycleGAN thing. So the sort of red stuff that's labeled A is the noisy EEG data. The blue stuff that's B is the clean EEG. And so we've got exactly this kind of thing going on, right? So it looks like conceptually that it's going to work really well. The problem that we found was that, so think about what's going on. I'm taking noisy EEG data. I'm going to remove the noise. And then I'm going to say, okay, now I want you to reconstruct the noisy EEG signal, right? So if this thing is clean, this guy has no idea like what kind of noise was there before or where to add it. And so I think what happened early on was that just to make this thing work, it would go, okay, I'm going to take the noise out. I'm going to leave a little bit of noise in there so that you know how to reconstruct it when you come back over, right? So it just wasn't as effective as it needed to be, because to go from the noise-free domain back over to the noisy domain, it had to have some hook, right? To know like, oh, the noise is here. And so we weren't getting exactly the results that we wanted. So, oh, and this is like my favorite slide in the whole presentation. So this is the problem, right? So the clean signal is the horse and the background is the noise, right? So we would go, oh, okay, that's awesome. We can actually remove the noise. We've got the horse sitting right there, right? And then we go, okay, let's add the noise back in, and we wind up with like waterfalls and flower gardens and stuff like that, right? So it just wasn't good at like coming back around, because if you clean it up completely, you add in this other stuff, and it didn't look at all like the thing that you started with. So the intuition was to build this thing called an asymmetric GAN, and the idea is that we're going to put another network in there that actually learns to extract the noise, right? So we're going to explicitly pull that out. We're going to say, I want a network that can take that noisy signal and go, oh, you give me the noisy signal, I'm going to produce an output which is the noise, and then what we can do is we can pipe that noise back in so that when I take the clean signal, I can join it up with the noise that I actually produced. So it looks like this, right? So we've got the network that goes, okay, here is my horse in its original background. I'm going to denoise it, and I get the horse that's over there on the right. I'm going to explicitly pull out the noise so I get the background that's in the middle, so that I can then join those two things together, and I can come back through the cycle and reconstruct this thing after. Okay? I know, I feel like I'm going fast, but are there questions? Yeah? Okay, that's good. All right. So now we've got this sort of asymmetric architecture. So it's not a sort of nice pure CycleGAN, but you've got different things going on in the forward and backward direction. And the architectures for these things look like this. The generator is on top, right? So you get an input time series and an output time series. It's all 1D convolutions, hyperbolic tangents, and the deconvolutions on the other side. And the discriminator is, again, doing convolutions, but leading out to fully connected layers and then just producing a single kind of a bit at the end that goes real or fake. So fairly standard architectures. Okay, so let me just talk about the evaluation briefly, tell you how well it worked, and then I'll wrap up. It turns out that evaluating this is real hard, right? So in essence, what we're doing is we're saying, hey, we've got some noisy EEG data. We would like you to denoise it, right? And so what I'm going to do is I'm going to say, here's my denoised EEG data. Now, how do I figure out if it's been denoised properly, right? So we could, if we wanted to, try and hand it to human experts. It turns out that the neurologists at the University of Maryland Medical School are super busy and they're very expensive. So we're not going to do that. So we did a couple of things. One is we created a, does it say that for the ground truth signal? Hang on a second. Okay, we created a synthetic data set. So we did something actually rather similar to that thing we saw earlier from scikit-learn, which is we've got sine waves and square waves. That's going to be our clean signal. So we're going to take a sine wave and a square wave. They might have different periods. Then what we'll do is we'll do linear combinations of those things. And then a noisy signal is a linear combination of a sine wave, a square wave, and a sawtooth, right? So in essence, we've got the sine wave, the square wave, or the clean signals, and then we throw a sawtooth in there, that's noise. We had 4,000 signals in the training set. We had a validation set of 1,000 and a test set of 1,000. And here are some of the results, which I think look kind of nice. And we'll see it actually applied to real EEG data in a minute. So what you're seeing in that sort of top plot is the signal with the artifact, right? So we've got these sort of superpositions of sine waves, square waves, and sawtooth waves, right? Here is the noise signal that was pulled out by the asymmetric GAN. And the noise signal was the sawtooth wave, right? And then over here, we've got the actual clean signal, and then the signal that was cleaned by the asymmetric GAN, right? So you can see that the asymmetric GAN is like leaving a little bit of those like wobbles in there that are still caused by the noise, but it's getting the structure of the signal to be to look good. Actually, if you look at the MSE, or the mean squared error between the ground truth clean signal and the denoise signal, it's actually quite low. So we feel like on average we were doing a good job of pulling out the noise. And then we also did some work on another one of these Army Research Lab data sets. And we did a couple of things. One is we just kind of eyeballed it and said, does it look like it's doing the other thing, the right thing? And then the other thing we did was we used an artifact detector, right? So the idea is we've got these systems that were trained up in a supervised mode to go artifact or no artifact. And the thought was, if we can take a noisy signal, clean it, and hand it to the detector, and the detector goes, I don't see any artifact, then we're doing pretty good, right? So we're trying to see if we can get past the artifact detector. So here's an example applied to, I don't know if this is eyebrow raising, maybe it was eyebrow raising, but here's an example where the original signal is the purple one here on the left. The clean signal is actually the sort of pinkish signal, or red, I guess that's pink, which you see here. And then the noise signal is what was pulled out over there. So you show that to neuroscientists and they go, yeah, that looks like it's doing the right thing. And then if I'm just going to jump ahead to a couple of slides on the evaluation. The artifact detector, so if I just give noisy signals to the artifact detector, or clean signals, it's accurate 97.39% of the time. So the artifact detector is really good. It can go, yeah, there's an artifact in there. The denoise signal that we gave, so we took noisy signals, we handed those clean noisy signals over to the artifact detector, and it said they were clean 72% of the time. So we're not perfect, right? But I think we're doing a pretty good job of trying to get rid of the noise. All right? So, okay, so in summary, what we did was we took that sort of, again, kind of Frankenstein system that was super painful to actually fit on low power hardware, turned it into a neural network that you just kind of train up end to end, right? So I get some clean data, some noisy data, boom, right? You sort of let the GANs do what they're going to do. I would say I think that the downside to that approach is that the GANs are, they like to be unstable, right? So it turns out that the discriminator often just wins. So think about it this way. All of us in this room, I think, we can go to a movie theater and go, that's a good movie or that's a bad movie, right? But creating a movie in the first place is real hard. So in some sense, the generator is trying to create movies, and we just sit around and going, that wasn't that good, right? So the discriminator has a much easier job, and it turns out the discriminator can get really good really quickly, and it can get so good that the generator goes, I can't win. I can't figure out how to make traction on this thing. So it took some time to try and make that thing work well. However, the mechanics of it, right? So the algorithm is basically back propagation in neural networks, and so the hardware folks kind of have it's like one algorithm that they have to make work well on the hardware. It's not like it's thinking, I gotta have this support vector machine and stacks and all this other stuff going on. So they were much happier. All right, so I'm gonna declare victory because it's getting late. And hold on. Let's see if there are any questions. Yeah.
So just kind of maybe a naive question. You know, there's a huge investment in the image processing, CNN inside the house, right? Hey, have you guys ever contemplated to use CNN kind of thing as a detector or whatever, help out someone?
Yes. So we are actually using convolutional neural networks, but we're using one-dimensional convolution, right? So you've got the signal through time, and we're doing convolution through time. I can't remember. So Sunil, did any of those guys in Tinusha's lab do they try and treat those things as images and do any 2D convolution? Didn't one of them do that?
Yes. Yes.
Do you want to say anything about it?
One of your layers
There was a
showed 2D.
Yeah, that's probably because we had multiple filters and then it turned into a 2D.
Yes, so there were a bunch of, there were papers where there was a guy in our lab as well, Jingwang Wang. He basically literally just took a time series, converted it into an image and then did it and treated it as an image and did
Just standard 2D convolution.
2D convolution.
Yeah.
And then in the lab earlier there are other people who did 1D and 2D convolution over the time series and then tried to get it working. But they did it for EEG detection.
So not to solve the actual problem, but maybe solve bits and pieces of problem, like as a detector or something?
So we've definitely got convolutional network pieces in it. Yeah. Yep.
And it's along those same lines, you know, like accelerometer, right? A lot of I will think it's like a simple task for accelerometer too.
Yeah. So they've got sensors that they can actually put near the eye and try and figure out what's going on. But then that's just sort of another thing that you have to deal with. You get and so if that thing comes loose, then you're dead in the water, right? So that's where you've got these reference signals. So if I've got a reference signal that goes, okay, you're blinking your eyes, then I can take that signal and try and back it out explicitly. But then again, if that's not working, then your EEG signal is completely. So we were trying to get away with less information so that we could kind of move into a setting where it's more ambient. Yeah, did you have a question?
Yes, so I might have missed this, but how is the EEG detector actually made? You said like the accuracy was like 97 point something.
Oh yeah, so that was all trained up. That was a supervised thing, right?
Oh, okay.
So what you do is you take the EEG signal, and it's been manually labeled as in clean, noise from here to here.
Okay.
You pull windows out, you just treat those as positive and negative instances.
Oh, okay.
Yeah. Yep, Dennis.
One thing we used to do in the Navy, I know you were working with the Army, so it's a different
Right.
world, but we would do towed arrays using these same techniques, but using Fourier transforms.
Yep.
Have you thought about taking on a different employer?
Oh, sure. If there's anybody in the Army who wants to give us, or Navy, we'd be very happy to take the money. So the idea of doing Fourier transforms, so there was that bit in there about wavelet transforms. So the issue is that the noise may or may not fall into specific frequency bands, right? So it can be spread across multiple bands depending on the kind of artifact.
Well,
and so
what we were doing is we were trying to do ICA on components in submarines and ships.
Right.
And specific devices that would give off certain signatures. So we would do signature analysis based on all the different frequencies.
Right.
But we have thousands of ships that
Right.
at the same time because it's a noise source.
Yep.
But we're getting 98% accuracy over 1,000 months.
Yeah. Okay. Yeah. We should. Maybe we and I should connect and talk about it a little bit more to see if there's a mapping
It's
between.
been a long time.
Okay. All right. That's fine. Okay. Other. Yeah.
Two things. For the cycle again, you were talking about how basically what I imagine is that you map from A to B and then B back to A, right? Or A prime, right?
Yeah.
So you're saying that is it inherent in the nature of the cycle again that error term that you're trying to maximize on, that it just has a threshold value that it just doesn't go underneath?
Well, so right. So the idea is that if I'm taking images from one domain and applying some transformation to them, right? I don't want it to be the case. So again, I think the example that I mentioned, but I probably went through it too quickly, is I got a horse,
right?
And I want to turn that into a zebra, right? What I want is to preserve the other context that's there, right? So I don't want to be the case that the mapping in this direction essentially just kind of ignores the data I gave you and just says, here's a nice picture of a zebra, but it really doesn't look anything at all like this, right? So what the CycleGAN does is there's a loss associated with, I would like to produce an image over here that fools the discriminator, the zebra discriminator, because this guy is trying to say, did you just give me a real picture of a zebra or did you give me a fake picture of a zebra? So part of the loss is, how good is this discriminator doing? Another part of the loss is if I go from horse to zebra and back, how far apart are the things, right? So that forces me to actually say, I need to maintain some content here so that when I come back around, I'm like in the same neighborhood.
Right, so I think my question is that that the issue you were facing with having the artifacts in there where it was getting back to the final picture with some of that history in there that was, I guess, necessary to bring it back.
That's right.
Is that natural to that algorithm, or is that just simply something?
Oh, I hear you. Right.
Like, is it just a flaw in the algorithm itself?
So that's you mean in the sort of the CycleGAN approach?
Yeah, exactly. Yeah, is that?
So I think for us, so no. All right. Good question. So I think for us the issue was that we were actually trying to erase part of the content, right? So in that sort of horse to zebra back to horse thing, all I'm doing is I'm taking that horse and trying to turn it into a zebra and keep everything else, right? So then I've got all the context here, and then I just need to take that zebra and turn it into a horse. What we were doing was saying, I want to take this noisy signal and erase the noise. And then now there's just no information here as to where the noise was. And so coming back this direction, it was like I don't know, right? Like I can add noise, but I don't know where to put it or what it looks like. So I think it was that we were subtracting like our goal was to get rid of information that made it impossible for us to kind of reconstruct it appropriately. It's a good question. Yeah. Okay. Okay.
Dr.
Oh yeah. Yeah. What's that?
You mentioned like the discriminator being too good. How do you combat that? Do you just like kind of train it initially?
Can I do something that's very rude right now? Florian, can I get you to answer that question? Okay, so Florian is an expert in deep learning. Sunil can answer that question, but Florian, can you help us understand what do you do if the discriminator is crushing the generator?
I mean, it's hard, right? It is what happens because it's just the easier task. So like one of the things that might be interesting in a situation like this is that you start both of them out with like really low capacity, and then as they reach the equilibrium, you start like progressively increase the capacity of both of them. Because just like since the discrimination is so easy, it's likely to just like crush the problem. But if they're both weak at the start, they're likely to stay balanced for the long term.
I see. So you can, for example, give the generator a little bit more capacity because it's a harder problem.
Yeah, so like you can build them, put each of them up layer by layer as they reach equilibrium.
Okay, I apologize for putting you on the spot, but okay, good. All right.
Yeah. And what like framework did you use?
Were you TensorFlow, Sunil? PyTorch.
Yeah, PyTorch.
PyTorch. Okay. Yeah. Okay. All right. Well, thank you very much.